apropos of the topic, sailing is one of humanity's oldest applications in physics, as you might guess, utilizing the interplay of fluid dynamics, aerodynamics, and structural mechanics to propel a vessel through or above water. So, just to make it a little more boat centric, I have small pictures of 5 boat types. They're be presented, from newest to oldest. So hopefully you can all see this hydrofoil. It's a catamaran, which is fairly obvious. There's 2 pontoons. You can also see from the pontoon on the right, there's a tube, and that goes to a foil, which is in the water. Looks to me like they have the one on the other one up, which they do, and at times. And you can see a bit of the rudder, which has a foil attached to it. So these hydrofoil catamarans were perfected in the late 1990s. They're now the America's Cup chosen boat, and they're made of exotic materials. If you happen to have $300 million, you too can have one. And exotic sails. One in the middle, you can't tell, but it's called a wing sail because it's about a couple inches thick and more like a wing. And it's steered with a rudder, but the rudder has foils. But the writing of it is done with foils and extremely exotic computing. The first ones they built were the foils were passive, but now they control they keep the boat from tipping over. In fact, the second one, it's a little cheaper. It's a windsurfer. You probably could tell. They were invented in the 60s. As I said, this is from newest to oldest. And it's got a, I don't know if you'd call it a hull, but it's a surfboard sort of, but it's a planing hull. I'm going to call it a hull. And there's a dagger board. You can't see that. But if you want to sail into the wind, you need something to keep it from going sideways, as are required for all sailboats. And you can see it's got a wishbone spar. Well, you can't. I don't know if you can see it. I can. He's holding on to it, and it helps shape the sail. And if you're very good at this, doing it in 50-knot winds, I've seen people do it. You have a harness, and so you don't have to hold on to the wishbone for such a long time. And the third one is kind of a unique boat. You don't see too many of them. It's called a catboat because the mast is in the front, and it's got a wishbone spar, and okay, it's an aside. The wishbone spar has one notable advantage over a boom, which is it won't kill you. And you may think that's a joke, but it isn't. Every year, probably a half dozen or a dozen people kill themselves with the boom, with a flying jibe. And the wishbone spar won't do that. So it does have its advantages. This was made popular by a company called Freedom Yachts, if anyone's ever heard of them. The next to last one is out of the water. It's a cruising thin-keeled probably coastal cruiser. It looks too small to go out into the ocean. It's got a high aspect sail. It's hard to tell. I can tell, but you probably can't, that it's a cutter rigged because it has two what would you call them? Well, the
fins
lines
in the water.
Hmm?
Fins in the water underneath.
No, it's the I'm blocking it. Okay. There's shrouds on the side and stays. There's 2 forestays, and there'll be one in the back or 2. And you can see there's a fin keel at the bottom, which is very important if you're a racing boat. It's also very helpful like my boat, I have weighs about 11,000 pounds, and 6,000 pounds of it is lead in the keel, and to keep the boat upright, if or at least not flip over and put the sail in the water. And finally, um, I consider one of the more interesting cases is a lateen sail, that a sailboat. And this is a small one. It's obviously a drawing, um, but it was developed in about 200 A.D. In other words, human beings have been sailing into the wind for almost 2,000 years, um, which was a surprise when I ran across it. Um, and so it's not new that we can go upwind, which the after about 300 years, they were common in the Mediterranean, and they got much bigger with 2 and 3 masts. And in about 1500s, the Portuguese adapted it to their caravel, which was the boat they used to explore the world. So on to the next slide. So here's the agenda: basic sailing terminology, basic boat physics, physics of the, as you can see, 3 marvels of sailing, which I consider to be sailing into the wind, sailing faster upwind than downwind, which is, I can testify that I experience that all the time sailing. Um, then we'll look at hull types. The fourth one, hydrofoils, um, is, I consider, Marvel 3, because it can go 2 to 3 times the speed of the wind, and which surprises me a bit. And I can accurately say that a hydrofoil never, ever sails downwind. If anyone doubts that, I'll explain why in a little while. Then keel type, sail plan, hull materials, and heeling and heavy wind tactics. I have a feeling I'm not going to get to all of this, but I certainly want to get to the 3 marvels, and brief design discussion. So basic sailing terminology. You can see the term sail, hull, keel, rudder. I hope everybody know what that means. Just this was actually an excuse to put in the notion that sails are concave triangles, concave on the windward side and convex on the leeward side. And that's critically important because they function as an airfoil, like an airplane wing. Um, and the convex, concave aspect can be the result of the wind usually, but battens or built into the sail. That particularly is true for the hydrofoil, where the sails are really, really high tech. So below the waterline is the hull and the keel that resist sideways motion. So you go into the wind straight instead of side slipping. Since water, I want to mention that water is about 800 times denser than air. And so the small keel you saw in that boat can actually not only keep the boat from going sideways, but as we will discover, it's a foil, and it provides considerable force pushing the boat, uh, resisting sideways motion. And I'll probably mention again, if you doubt that, I can make it happen and make my boat go sideways if I want to. But obviously, I try to avoid that. And then there's obviously the mast boom, the running and standing rigging, and many other parts to spend lots of money on. So first, and it's easy to overlook, but sailboats all share one physical trait, which has to do with physics buoyancy. They float, one hopes. And the explanation of this is the Archimedes principle. Probably understand that, so I won't go on. But at this point, I want to ask everyone. I remember, he's passed away, but he gave our first presentation on AI where he had it, I think it was ChatGPT, create a plus paper on the Archimedes principle. Does somebody must remember his name? No, is anybody there?
We're here, but I don't know.
Barry Court.
Hmm?
It might have been Barry Court.
That doesn't ring a bell because he hasn't passed away, has he?
Yes, he is. He's gone. I'm sorry to say that.
Oh, okay. Uh, so, and the vast majority of sailboats, I mean, this is what I considered common knowledge. These two is a displacement hull, and it's well known that it can't go faster than the square root of its waterline length times 1.34. And it's because it pushes its way through the water, creates a bow and stern wave, and getting out of those waves takes a huge amount of power, which no sailboat has. I mean, my engine is like 25 horsepower. I mean, I own a 35-foot Pearson sloop rigged with a smaller keel with a bulb at the bottom. So 3 marbles. Uh, so we already know sailing involves fluid and aerodynamics. And the 200 AD for the Latine, which surprised me. So we first examine our sailboat. Example, a Latine can sail upwind, referred to as Marvel 1, and then even more mysterious how a displacement sailboat routinely sails faster upwind than downwind, and yet even more mysterious how a hydrofoil can go substantially faster than the wind. So, I mean, I don't know if anybody understands this already, but I'm going to keep going. I didn't.
Well, I have one comment because
Sure.
I'm not too smart when it comes to sailing. Now, when you say downwind, you're going with the wind, right?
You've
And what's the definition of upwind and
no.
downwind?
The difference I didn't say it intentionally. I am saying the wind the helmsman perceives,
Uh-huh.
not, I didn't want to jump into true versus apparent wind until I get there.
If I might contribute here, from a pilot's perspective, going downwind is when the wind is at your back. Going upwind is when the wind is in your face.
That's what that's what I wanted to find out. Okay. That's
Yeah,
exactly.
and but I'm talking about a the helmsman, not a person standing next to the helmsman, which would be difficult. But because when I said the hydrofoil never goes downwind, what I'm saying is it always goes faster than the wind. So the helmsman is perceives the wind coming from in his chest, and it's coming from the front.
Yeah.
30, 40 miles an hour. When the back wind is back, if he stopped, would be going 20 miles an hour, which is
Okay.
one of the new developments. And I'm not going to go into it, but I just mentioned that it's changed racing tactics dramatically with those kind of boats. So at first we suppose a boat with only a jib or Genoa, which Genoa is just a large jib that overlaps the main. To match the diagrams I lifted from a classic book on sailing, and, and actually people do often sail with just a jib in heavy wind. Now suppose the wind is dead ahead, i.e. from the pointy end to the back end, and you're standing still. Obviously the boat's going to go backwards reasonably straight for a little while. Now, suppose the wind backs. I'm using some sailing terminology, but what that means, if you're looking down, it rotates 45 degrees counterclockwise and veers going the other way. So now it's on the port side of the boat, and the sail is allowed to move only a bit to starboard by the jib sheet. The sail now takes on the shape of a foil, and the windward side is concave and the leeward side is convex. The boat starts to move forward into the wind, actually 45 degrees off the wind, and how, I mean, I just one wonders, people have wondered for, thousands of years now, how can that be? Um, so, so the, this discussion starts with how this happens, uh, with the well-known Bernoulli principal Venturi effect pictured in the diagram on the next slide. So we'll just go to the slide. I'm going to be here all day if I keep going at this rate. So here's the classic picture of the Bernoulli principle, and the Venturi effect is the constriction in the tube. And as you get the red lines I added, and the sideways force on the tube are much higher where the air is going slower, and where it speeds up through the constriction, it is much less. Okay. So using, you might wonder why I would jump to the Bernoulli Venturi, but and I wondered about it, but it's hard to understand any other explanation, how a forward force could be generated from a wind going the other way. So now we start a part I invented. I didn't find this in any book, but I think it helps to explain how this works. And that is, if you have telltales, numerous ones as I have, affixed to the convex side of the sail, I have one on all sides. What they do, I'll explain what they do now. They show you how the air is flowing over the sail. Ideally, on both sides, they are firmly affixed, pointing straight back to the sail, showing a very uniform flow on both sides of the sail. And one of the beauties of it is now you've got the right angle, correct angle attack. If you go a little upwind or downwind, and you get it wrong, they will start going up, down. One of the beauties of them is that what they do tells you how to correct it. The other thing, and the reason this occurred to me, is when that goes up, the boat slows down 1.5 to 2 knots. It's very noticeable. So my take on it is that those telltales are showing you what is creating the forward force. And when they go off, you slow down. When you get them back right, correct, i.e., streaming perfectly parallel with the wind direction, and you can see they are absolutely glued to the sail. Then you start going, you might be going 6 knots. Now you're going 3.5 or 4. All of a sudden, you're going 6 again. So now back to the presentation. So we know we have some forward force. So it's either got to be on the windward side of the sail or the leeward side. The windward side is the concave side. And as it will turn out, we'll find out the major part of it is on the leeward side, somewhat surprisingly to me. And And also, given that, but we don't know that yet, but we now posit on the leeward side that the air speeds up dramatically because we're at a loss, because we basically want to apply the Venturi-Bernoulli principle to provide a lift to the sail and pull us forward. The word sucking is used a lot too. So sure, the Arabs didn't get this, but they still sailed into the wind. So now, why would the air next to the sails speed up so dramatically? And keep in mind, this applies to airplane wings, and it also applies to baseballs, soccer balls, all spherical objects when they start spinning. The curveball is explained by this phenomenon, which surprised me when I discovered that part of it. So first, I'll quickly go through. There are two common but bogus explanations. I suspect most of you have heard them. And here I mentioned that the angle of attack is critical for this to work. It's within a degree or two either way. But the nice thing about the telltales, as I said, is they tell you how to correct it. So here, this is actually a picture from a classic sailing book, and it was intended to show a wing, but I'm saying it's a jib, and you're looking down at it. And basically the air speeds up on this side on the leeward side of the sail, and slows down on the other side, and you get lift pointing in the direction, enough of it in the forward direction, given these the two blue larger vectors. So here, well, the preceding diagram, so now we're going to see the bogus explanation, which you've probably heard many times. So the basic notion is that the air, this is actually for a wing, but you'll see that it doesn't apply so well to a sail, but people give it anyway. In fact, when I asked AI, it was the explanation given, surprisingly enough. That was not ChatGPT, that was Google. So the basic notion is that the air molecules split at the leading edge of the sail. Nobody disputes that. But that they have a compelling need to rejoin their mates that went below that go below the sail. So the rejoin happens at the end of the wing, or sail in this case, and thus the molecules on the top or convex side travel further and must travel faster. And given Bernoulli and Venturi, the air would have gone through a narrow tube and would provide lift, and the boat goes forward. And you can see it's kind of the intuitive for a wing, but it makes no sense for a sail where it's the same length. And in reality, none of it makes any sense. It's not clear to me why this explanation is ever given or gained traction, and why someone thought they needed to rejoin. That makes no sense either. And would they, even given this scenario, would they travel fast enough for a wing or sail to provide lift? So the explanation lies elsewhere, and I make a dig at AI that it could provide this explanation. I remember doing it and told it was wrong, and gave me 5 more bad explanations. When I got to ChatGPT and Claude, I I didn't do that. I started giving it hints to help it out. With Google, I didn't. So here's the air barrier explanation. That's the second one. The first one I call rejoin, and here's the air barrier. And so you can see the air barrier is above, and the theory is that the wind goes through this under the air barrier, which is immovable in some sense, and goes faster near the sail. So once again, they split, and the air splits. And this was hard to believe, but the classic sailing book gave this explanation. And AI also gave it. And so now the tube comes into play, the air speeds up and provides forward lift. And but when I looked at this the first time, I said, wait a minute, how can this sail provide much lift at the last 2/3 of the sail? That doesn't make any sense. I can see it doing something at the beginning. And if you know what the real explanation is, you would realize that it just can't be correct, because that tube has to be incredibly small for the air to speed up and provide the lift to get a jumbo jet off the ground. So this is bogus as well. Now so we're at a loss. We're back to no rejoin, no barrier, same diagram. You've seen it 3 times now, except for the wind barrier comment. So here's the accepted explanation. And I don't know if anyone knows this, but I was somewhat surprised to discover that the theory this is based on is 120 years old. And there's no dispute that it's the theory that applies. It also applies to those baseballs and soccer balls. And so it's a pretty important theory. So on the concave, so once again, the air is flowing into the sail and splits. On the concave side, the air spreads out, and but it still actually pushes the foil if you look at the vectors involved. But as I think I mentioned it before, about 3/4 of the force on an airplane and a sailboat is supplied on the leeward or convex side. So now we get to the heart of the matter. Now consider this crucial flowing air / fluid. Applies to all fluids, water, air, that are kind of at their normal state. Wouldn't apply obviously to frozen air. So moving air or any fluid close to a convex surface tends to cling to the convex curvature following lower pressures as long as the curve is not too great. And this is known as the Kanata, I hope I'm pronouncing that right, effect. And it's pretty well known. You can demonstrate it yourself. If I'll tell you how, not right now, but with a spoon, if you care to. So it turns out we now have the situation described by the physics Kutta-Joukowski theorem, which is the one that explains sailing, flying, baseballs, soccer balls, whatever ping pong balls. And it's a fundamental theorem of aerodynamics. It was developed in between 1902 and 1906. And it determines well, I guess it's probably on the, so I might as well go to the next slide. What this theorem predicts is a pressure gradient starting at the sail wing. The low pressure is next to the sail, and the gradient moves away from the sail or wing. The logical chain, as the book said, is the curve geometry forces the flow to bend. Due to that Kanata effect. I'm not sure I agree with the word forces there, but it certainly bends. Bending flow requires a pressure gradient. The centripetal argument. Next slide, which I also have a slight problem with. The low pressure develops along the convex surface. Air accelerates into it and along that region. And the theorem correctly describes the velocity and pressure you observe at every point due to the Venturi-Bernoulli theorem. Now, that strikes me as the heart of the matter, that this theorem predicts exactly what happens in an airplane wing or a sail. And so leaving that for a moment, even better, once the split air follows that pattern, it attracts increased volumes of air and speeds up even more. So, and the split moves further in front of the foil. You may have noticed I switch between wing, sail, and foil quite a bit. And because somehow you have to explain how the air speeds up so much that I always think of the jumbo jet. How can that jumbo jet get off the ground due to this effect? And that would imply a huge amount of air goes through an incredibly narrow channel to provide the lift to get the airplane to go up or our little sailboat to go forward. One of the nicer, or the more important parts or beneficial parts of this, that the lift is proportional to the airplane square. I said airplane there because the square of a sailboat velocity isn't so impressive, but the square of a airplane is enough to get the job done, obviously. So the centripetal line, I'm going to go through this quickly because it seems to me it doesn't really help much. So air parcels flowing over the convex side. I'm on the third one. You know that the air molecules parcels move in a curved path bending around the surface. I should mention at this point, looking at this myself, forgetting all the reading, and I kept waiting for the word vacuum to appear. That seemed to me to be the explanation, that the vacuum appears next to the wing and the air rushes through there at a greatly accelerated speed. I never found the word vacuum, but I think on the next screen you'll see low pressure at least. So that was my intuition that 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 for the air to speed up as much as it does, it has to go through an incredibly narrow gap, in my opinion. So something pushes those parcels inward, those molecules. What provides that force is a fluid. It's not traveling a greater distance that does it, or the air barrier. And the only thing we can hazard a guess that would do that is a pressure difference just above the wing. So so they say the pressure gradient, this is in a book, nudges each air parcel inward. So the conclusion is unavoidable. Low pressure at the surface is not optional, it's unavoidable. What they're saying is that pressure gradient is unavoidable because the air follows the wing. So I guess, so that seems to be an intuitive explanation could be helpful. Well, at least certainly help me. And this is what, I couldn't really find one, but this is what Claude had to say about it. the I'm just going to read it because basically the fluid layer next to the foil surface is slowed by friction, and the moving stream drags along or entrains the fluid around it via viscous shear. That's what I guess, and away from the surface, entrained fluid can be freely replenished from the surrounding reservoir, but in the thin gap between the stream and the surface, there is a limited supply of fluid to entrain. In other words, there's a surface there. So the surface is what prevents that narrow flow of or air or to speed up, because there's only one supply of it above. So the gap, or they call it the gap, gets depleted faster than it refilled. So pressure drops. Lower pressure on the surface, this is of the wing, means that net force pushes the stream toward the surface. It curves and this is sort of an explanation of the canola effect, which is what I was looking for. And it speeds up. The cap is very narrow relative to the amount of air entering the stream. So that was the best I could find that explained it at a lower level. So looking at that, I had a theory. Suppose the wing turned into a screen, what would happen? In other words, I asked it if many small holes developed on the wing. And we now know that the upper or leeward side of the wing supplies 75% of the, or 80% of the lift. Thus, the resulting holes, if it became like a screen, it said would be catastrophic. And if they're situated in the front of the wing, the plane will go down like a rock, which that I accepted that. So just here's the formula, just in case you're wondering what it is. But if you look up I call it the KJ formula here, it it's half of air density, velocity squared, area, and CL. If you look it up in a book, it won't have a V square. It will have something over here that C is the velocity times what we call CL, which is the lift coefficient, depending on the angle of attack and the wing shape or sail shape. So, but I wanted to put the V square because it seems that's what I would guess really helps airplanes to get off the ground. So this is a kind of useless slide, but it shows that once the flow gets going, it greatly increases because the split moves further and further in front, and more air has to go through that small gap, which is important for providing more lift. So now back to sailing. What time is it? Yeah. Steve, do I have any time limit here, by the way?
No, not at this time.
Okay.
That's not meant to be a pun, but I guess it is.
So, as I said before, the difference between the optimal angle of attack and turbulence is a couple of degrees either way, 1 degree or 2 degrees, 1.5 degrees either way from where it is if those telltales are flowing correctly. So, obviously, for a jet wing, you can't really, not many of them allow for adjustment. I did find one, but it's not relevant here. But for for a sail, you can move the sail around by pulling on or easing the sheet, moving the block that the sheet goes through, the jib sheet, that is, or jury rigging additional lines to fine tune it. People do that more frequently than you might think. Or you could just re-aim the sailboat. And here are my sales pitch for telltales and how effective they are. And on my boat, I also have an apparent wind gauge So I use that to grossly aim the boat if I'm going upwind, and then I use the telltales to fine tune it, and usually just re-aim the boat as the telltales. If the telltales look good, I just keep going. If typically they either go up or down, and once I get into it, I know what that means I have to do, which is a plus. So here's a diagram of what happens if the foil is properly adjusted. This is from that classic sailboat book. This is pointed in the wind. It's luffing. Now you fell off a little bit. It's not luffing so badly. Here's the sail at the correct angle. You see they've drawn the wind parallel to or the air movement parallel to the sails. That's what the telltale tells you is happening. And at I have telltales at the front, middle, and back, and at all number of heights too, because air behaves differently at various heights. And so, and you might want to try to introduce a little twist or take it out of the sail to accommodate the different wind. So, and now we've, I guess we've headed up too much, and we get turbulence at the back, more turbulence. The back telltale would be going nuts at this point. And here, both this is, we've gone way too far. We probably lost, we're probably stopped or slowing down greatly. And the telltales are either, I forget whether they're pointing up or down and which side they're pointing. I relearn it every year. So, and there's also the adjustment of the sail draft and camber. I'm going to skip a detailed explanation, but camber is a length. It's the distance between a straight line between the front of the sail and the back of the sail to where it's to the sail. And draft is where that horizontal line has the maximum distance. And the rule of thumb is that if the winds are light, you want that the camber to be long greater. In other words, you want a belly in the sail, and you want the draft to be about 50% back, because with lighter winds, they will stick to the sail better. And then as the winds pick up, you take out the belly, in other words, reduce the camber, and you move the draft forward. And here I give a list of all the things you can screw around with, but I won't go into that. So now to the next very important topic. To me, looking at those diagrams, I wonder, why doesn't a sailboat just go sideways, mostly sideways force? Well, we know now it's because the predominant force is the force forward, mostly forward.
Bob, can I ask a
Yes,
quick question?
sure.
If I follow what you're saying here, you can maximize the speed that you have depending on the direction that you sail into the wind. In other words, if you want to go at the fastest speed, there is a faster and a slower speed as you're sailing into the wind, correct? And
Yes.
if so, how do you adjust the sail for that?
Just you try to get those telltales to lie perfectly flat. And we're going to see a slide in a few minutes that what does it do? Oh, it graphically, it shows why that you actually go upwind faster than you go downwind, and what's the fastest point of sail.
Yeah.
Um,
Thanks.
okay. So, so now the question, why doesn't a sailboat just side slip? I'm not going to explain how I can do it, but when I do it, well, basically I just come about too sharply, lose all way, and the boat starts going sideways. Thus, when I come about, I usually stop 10 degrees short, get some speed up, and we'll see why is that important. And it's the keel that does it. And it has two ways of doing that. One of them more important than the other, I guess. So here's a diagram of the obvious way the keel prevents side slip, and the hull. That this here's the sail force of the wind, this wind on the sail, and up here is the force resulting at the keel, which has a forward component. Looks kind of small there. I don't think it really is, but this is a diagram from that classic book. Once again, now we get into the but surprise, I didn't realize this was so insignificant, but what's called keel lift, which is the next slide. So the answer to why the boat doesn't go sideways is basically this one, that the keel is a hydrofoil itself and generates lift. So I'll just explain the slide instead of reading that. The green is the keel lift. And the significant piece here is the blue line. The boat, you think the boat's heading this way, but it isn't. You're side slipping to some extent, and different boats side slip more or less. But the side slip means that the water going over the keel provides lift, because if you think about it, this is exactly the same as the air going over the sail. The water goes over both sides of the keel. It speeds up on the what would be the leeward side of the boat, and thus you get lift. And so the sailboat goes not only what did I say? Oh, not only do you just get the resistance of the boat and the keel trying to move through the water sideways, but you get this lift from the water going faster on the leeward side. No, it's the windward side. It's going faster on the windward side. I'm sorry. And that causes considerable lift. And as I said, it's very demonstrable on a boat. If you stop it, it will go and I don't do it intentionally, but every so often I screw up coming about and the boat starts going sideways. And I wish I had not turned so sharply. So it's a real effect, and it's important. And remember, the water is 800 times denser than air. So looking at that KJ formula, the force developed by keel lift is significant.
So Bob, how do you adjust the rudder when you're doing all these operations?
When you come about, you dust the rudder. And as you're sailing along, you tend to adjust the rudder because, say you're doing a 10-mile leg, you tend to move the rudder around. You're trying to sail the course, but that's impossible to keep the boat within about 10 degrees either way of the exact course if there are waves and currents and whatever else interfering with your efforts. So yes, the rudder, I've never seen any write-up of rudder lift. The keel is in the right place in the boat to provide lift. The rudder is at the back. And But now that you mentioned it, it probably would.
It's
But-
not shaped like foil. It's shaped like a centerboard. It's straight. It doesn't have a foil. It's
Say
like a
that
center-
again.
It's like a centerboard. A rudder and a centerboard have the same configuration. They're flat, so they don't have a foil effect, unlike a keel, which is not flat. Keel has shape of a foil.
Yeah, the keel, if you look at a keel, it isn't very impressively shaped, but it is rounded at the front, but it doesn't bulge out because it couldn't, because it has to work on both sides, on both tacks.
Wider at the top than it is at the bottom. Anything you do in water is going to be multiplied by 800.
Right. And in my experience, it's very significant. It is significant. As I said, I can demonstrate it. Anybody who wants to go on the boat and watch me screw up the coming about and then go sideways. And when you're doing that, you have to think about it. The resistance of the keel to go sideways is not changed because I'm not moving. So it's the lift resistance that's missing. And as I said a moment ago, it's very noticeable and distressing that what I did it. So if you've been following this explanation, this explanation, I don't know how many of you knew this. I didn't. The canola effect and the why the air accelerates. But it's been obvious since 1906. I don't understand why the rejoin and the air barrier explanation ever came up, but it somewhat humorously, I think you could state that all of this needs no explanation other than the Kanata effect, that this is what fluids do. This fluids going over a convex surface at the right angle develop that tube or gap where the fluid goes through very rapidly and provides lift. And baseballs feel it and soccer balls feel it. So enough of that. So now, Marvel 2, how is it that sailboats, mine included, go faster upwind than downwind? And I guess I'm going to move a little quicker here. And it's really based on the apparent wind. When you're sailing, so far, what I've shown the wind, it's the true wind, but the true wind is really irrelevant when you're sailing. It's the apparent wind that counts because you're sailing in the apparent wind. You're the helmsman, you're standing there, you're feeling the apparent wind. Your wind gauges are telling you the apparent wind, the speed, and the direction. So the apparent wind is a critical concept in sailing with both cruising and racing, particularly racing. It's the boat, it's the wind the boat actually experiences. And when I mentioned that hydrofoils never go downwind, what I really meant was to say they never go downwind with the considering the apparent wind, because suppose the wind, the true wind is 20 knots. Well, they're going over 50. So the wind that the helmsman feels is coming close to straight at him. So here we go. So this, I find it almost feels like to me that that the boat is making energy out of nothing. But in fact, the truth of the matter is I can demonstrate that you going into the wind, the apparent wind is faster going into the wind, and thus the wind is faster, and thus your boat can go faster. So here's a picture of what the apparent wind means. It's a very simple concept. You just take the boat heading vector and speed vector, which is the speed and direction, and push it in the direction, put it in the direction the boat's going at the end of the true wind vector. And now this is the apparent wind. And I guess the thing that surprises me is a bit the hydrofoil boats can go so fast, and the ice sailboats can go 5 times the wind speed. And just thinking, how can they do that with the wind coming right in almost right in their face? But that's the way the Canota explanation works. You can still generate more forward force, even though the wind is almost coming straight at you. Oh, I may not get to it, but the hydrofoil boats have extremely expensive sails that are built, and one of them is called the wing sail because it's more like a wing than a sail. And the reason they do it, make it, is because it keeps its shape almost no matter what. So, in other words, it can provide lift, even almost going straight into the wind. Lift in the direction the boat's going. So, this, the next slide shows the boat going, why the boat goes, or shows that the boat goes faster into the wind than downwind. In this picture, which again is from that classic book, the true wind is always 12 knots if you were standing there. And the apparent wind is shown by the downward arrow above the. So I'll just explain what it shows instead of reading. So here's the far left. I'm only going to discuss 3 of these. The far left, we're luffing 12 knots coming right at us. We fall off a little bit, and notice this boat only has a main, not a jib. The jib would change this and make the discrepancy a knot or 2 faster. But so close haul, the now going 6 knots this way, the apparent wind is 17 knots. And the boat is going 6 knots. And you fall off a little more, sailing between a close haul and a close reach, which close reach means halfway between 45 degrees into the wind and 90 degrees, in case you're wondering. And the boat's going 7 knots, and this is the fastest point of sail. Then we slow down a little bit, and then we go dead downwind, and the apparent wind is 6 knots, and we're going 5, which, I mean, 5 and 6 is 11, which is close to 12. And so this was probably taken from actual measurements. They didn't do it mathematically. But I can personally testify that this is true, that when you go from here, the 7 knots, and go downwind, it's like all the joy goes out of sailing. You feel like you're going, well, 1, this way, the wind is coming at you at 50 knots, and that's exciting. But 2, you know you're going slower. And did I mention when I was talking about telltales? I mean, I have a GPS that tells me my exact speed. That's why I know when the telltales start fluttering that the stream, the high-speed stream, has been affected, and I slow down. I'm sorry, I shouldn't have gone off on that tangent, and that's what led me to develop my own theory, which is basically the same as the ones in the book. And Claude came up with, Google didn't, but I didn't help it. ChatGPT I'm using probably an old one, but this theory has been around since 1906. So I think they'd have gotten it by now. And the first stab at it by ChatGPT was extremely weak. I think they may have even mentioned the rejoin one, but then I kept feeding it more and more information, and it eventually came around to the same explanation that Claude came up with right off the bat. So here's another game changer, the slot effect. So we've only been considering boats with one sail. Now we're going to consider, I'm going to move along here and just talk a little bit. So now I'm going to posit a sailboat with two sails, in other words, a sloop, or it's called a Marconi rig, a jib, which is a Genoa, and a main. And here's the diagram that shows it. And what it does is it gives a much greater air supply to the mainsail, which now can generate more forward effect. It's again the Bernoulli effect, but there's more air going through the gap. The Genoa isn't affected that much, but I always feel like my boat. I mean, I can look at the speedometer and it says a couple of knots faster at this point. And part of it is it's two sails instead of one, and part of it is this slot effect. But I don't know if I can successfully go back to this diagram. But if you put a Genoa in here, these speeds would go up by 2 knots or so. So this would be 9, but this one wouldn't change at all. So the difference would be considerably greater with a boat with configured with two sails. And so it just demonstrates how critical the apparent wind is. So now we'll go back. And I just thought this was a surprise to me. You go slower downwind, but there is some hope for a planing hull, which hopefully what a displacement goes through the water, planing hull skims along the top. And there is conceivably hope for a planing hull to go faster than the wind speed downwind, because if it flies a spinnaker, I thought intuitively that the spinnaker just gets pushed by the wind. But in reality, here's how it works, which is, and I always wondered, why do you want the spinnaker pole perfectly perpendicular to the wind as best you can do it? And you keep screwing around with it because the wind and the boat move around. But it's actually the same as a jib. You get lift from the spinnaker going around the edge and then the turbulence, but at the end, because it's not going to follow it all the way around. But in theory, you could conceivably this wouldn't help a displacement hull boat go much fast, or it does make it go faster. But what interested me is I found documentation that said you could conceivably make like a 470 or 420. If anybody's familiar with those boats. I'm trying to remember. I crewed on one, was doing the trapeze thing and the spinnaker thing, but we didn't have any way of measuring our speed. So now I'm going to move right along on hull types until I get to the hydrofoil. So the hull type is, the first one is displacement, which pushes its way through the water. And next we get to I'm going to go much faster, as you can tell. The catamaran and trimaran. The catamaran has two pontoons, and the trimaran has 3. The stability is achieved by the spacing of the pontoons. No big surprise there. If you capsize, you could be in trouble. If it's a large one, there's no way to right it. On the other hand, small ones have, like a Hobie Cat, have a wave piercing front, so they're more like a planing hull. They don't make a wave, so they can go pretty fast. There's others besides Hobie Cat, but a larger catamaran or the trimaran never becomes a displacement hull, but the catamaran does. The ones that you rent or charter in the Caribbean from the moorings are large ones and displacement hulls. And here's the formula for the stability. As somewhat of a joke, I said, working out, you see the cosine here of the angle of the pontoons, and it's not a real good idea to work it out for 90 degrees because then the stability becomes zero. And actually, I've done that, but I did it intentionally in a catamaran that had a big styrofoam ball up there, and I just wanted to see what would happen. And I managed to capsize it and get it right without even getting damp. But it's a lot different doing it intentionally and doing it when it's a surprise. So basically a planing hull is capable of rising out of its displacement wave and skimming across the water, like the windsurfer or the 470, which is
So Bob, a single
Yes.
outrigger, you see that on Hawaii 5.0. Do you have to be real careful for the stability on that? Instead of the two outriggers like you had on the prior slide?
Oh, you mean the yes.
There are two pontoons on these, right? There's a single outrigger, right? Which must be only stable in one direction.
Well, the outrigger is a different configuration. I've seen them, but I never paid much attention. You would think they'd put the outrigger on both sides and be a trimaran. Somewhat amazingly, in the very, very early days of catamarans, they didn't think that they could capsize. And when they did, the mast was pointing straight down, there was no way it was going to right itself, and people died as a result. And they started putting a hole in the trap door, some way to get out. I don't know what they do now. But you have to be, you do not want to capsize a catamaran, particularly a big catamaran. As I said, the little ones, it can be fun. So one thing about a catamaran, I'll just mention it, that they're very light and they have no momentum. I remember getting one down in Chatham and trying to land on an island. And I couldn't do it because as soon as I let sail out, I'd stop. So I ended up having to go into the island full speed ahead, which was a little disruptive to my health. So the planing hull is, so it greatly reduces wave making drag since you're on top of the water. And here's the formula of the lift to get the thing out of the water, I guess. And just personally, I've done this, particularly in the Caribbean, in Virgin Gorda, and going downwind. It was a 20-knot wind, and I was going like a bat out of hell, and there were boats anchored all over the place. And I discovered at that moment, steering a boat that's planing at that speed is non-trivial, because you've taken up the daggerboard to get to be planing. The daggerboard is essentially the centerboard or keel, which is really a centerboard. So now hydrofoils. And hydrofoils, the foils themselves, there's typically three, one at the middle of each pontoon, since a hydrofoil is also a catamaran, the racing kind. They do make regular type boats with them too. I've seen pictures of them, but I paid most attention to the racing ones and the America Cup ones. And so that foil, when you get going fast enough, elevates the boat, which doesn't weigh that much. As I said, it's made of exotic materials, carbon fiber, which is like weighs a third of fiberglass, but it's stronger, and the sails are much more exotic, and so that's how you can spend $200 or $300 on one. And here's the lift equation provide for, I guess it was for American. But if you look at it, it looks an awful lot like that theorem, the whatever, I can never remember the name, the KJ, or was it the JK? Anyway, that theorem that explains all of this numerically. And with a hydrofoil, you've got software that attempts to avoid the catastrophes that I mentioned here to keep the boat. There are things that can go wrong quite easily, and I've seen this movies of this, but it happened. The boat hit the deck, hit the water. If you don't come about properly, it will. But that doesn't sound too dangerous. Some of these do. But the thing I found interesting was the keel is replaced with the foils, and they control going in the direction you're aiming. And moving right along, it's called foiling now. As you might guess, has it fundamentally altered the strategy of sailboat racing, because you're trying to maximize your velocity made good. And I'll repeat that you never sail downwind. You'll always sail upwind from in other words, that wind I mentioned, the parent wind, is always going to be in your face. So not too superb. They're talking about close haul here, but the angle is typically 45 or upwind wind. For a catamaran, it's at speeds of 45 to 50 knots and 20 knot winds. The apparent wind is coming from in front of you, and so I don't profess to really understand this. I'd have to diagram it, but I do understand the notion that you're never going in downwind, because even going downwind, down true wind, you're still facing, in this example, facing 20, 30 or 40 knot winds coming in your face. But obviously it changes the notion of going downwind, because you'd absolutely never go straight downwind, because then you'd go 20 knots. But it go off a little bit and you're going 40 or 50 knots. So, and actually that does work somewhat for a regular boat like mine, because dead downwind, the jib is useless, or unless you go wing and wing, but go off a little bit either way. And you also greatly reduce that flying jibe danger, which is why I never go dead downwind. So that's enough of that. Drag. So there's obvious sources of drag: the hull resistance, the water, the viscous shear of the water. You're making the wave that creates drag, and there are other drags. So now keel type, the fin keel. How much time? Okay. The fin keel is the one you see here, and that's what you'll find on all racing boats of displacement type. And obviously it keeps the boat somewhat, mostly vertical, because as I said, on my boat, there's 6,000 pounds of lead in there, and the rest of the boat weighs 5,000 pounds. But it's also a foil, which causes the boat to sail you can sail much closer to the wind with a fin keel than with any other keel except for one I'll mention. But their directional stability isn't as good as with we'll see, a full keel. So here's the full keel. You can see it's much longer, doesn't provide nearly as much lift. But as I say here, traditional offshore passage makers favor this design for several reasons. One, notice the back is more, goes up and is, you can't tell, but it's narrower, but it's called a canoe configuration. One of my boat, when you're going downwind, the waves hitting the back, which is quite fat to provide good sleeping quarters, it is a very unpleasant motion. This boat, because of the heavy keel and the canoe back, it's called, would be very stable. It's also more stable because you're going to certainly put a wind vane at the back so you can steer at night and go to sleep. I also wondered, what do you do if a boat is about to hit you? Something else. But there's electronics nowadays that I forget their name that help a lot. So doesn't, but this is much stabler. Oh, the other thing did I mention? No. People sailing around the world and all across the Pacific almost never, rarely sail upwind. They always do it downwind. So the fact that you don't point as high is not that significant to them. They want a very kind motion in the sea. So here's a wing keel. My boat has a wing keel. It's shorter, but it does generate, it's like a fin keel, this part of it. And when it tips over, the wing part becomes more like a keel and provides some lift toward the leeward direction. This is where I get quite enthusiastic. I would love to have a boat with a swing keel. This is the greatest invention since sliced bread. You can see what it does. The keel goes down. In some cases, it's bigger and heavier. And the reason I like it so much is I chartered a boat once that had one, and I went out in 18 knot winds and getting bounced around quite a bit by the 1.5 foot waves. And I put the swing keel down, and it was like I waved a magic wand. The boat just went straight as an arrow. The waves didn't bother it. It just blasted right through them like they weren't there. It was quite an experience to feel the difference. It was almost like an America's Cup boat I sailed on once that's like, 65 feet long on average, and would have the same effect given its length. And it has the swing keel went down 10 feet. Their keel, the 12-meter keel, goes down 9 or 10 feet. So here I highly recommend these things, except when you have to pay to have them fixed or maintained. So here's another hydrofoil boat. I can't tell. It doesn't even look like a catamaran, but maybe it is. And the sails aren't, it has battens. I'm not sure that's a wing sail. This is definitely not one in the America's Cup. And here's a lateen rig. And think of Hobie Cat. In some designs, it was very difficult to come about because you had to move this spar from one side to the other. I think they came up with a solution to that. here's the standard Marconi rig, like my boat. And most production boats are now made with this configuration, although there are a few cutter rigs, which I would love to have. The main reason is because in heavy weather, you drop the front jib, you use this, the second one is a storm jib, you reef the main, and you're good to go. I'm trying to see if this boat has a wind vane, but I'm not gonna. So as it says, Blue Water Cruises like this configuration has quite a bit too because of its versatility. And here's the wishbone rig. The wishbone helps the sail take its shape. This is cat rigged, and because it says here it improves safety because you won't get a flying jibe, and it's associated with Freedom, which is the one manufacturer I was aware of. And here's a gaff rigged, which gives you better downwind performance, and you can see you can kind of make the sail more triangular by pulling the boom or whatever you want to call it at the top to make it more triangular. So it can be sailed upwind. And quickly, hull materials in 2 minutes or less.
Hey, Steve, you're good.
Basic-
You can take the full time.
Okay.
We're not gonna do anything else today.
I can sum up hull materials. Well, there's
fine.
4 kinds, and 2 of them are count, or 3. So let's see. So this discusses construction, and I make the standard joke that sailboats are a hole in the water in which to pour money, much as Mayan is, but because
Do you know who said that first?
yeah, I do. I think it all the time.
No, you know who said it first?
Right. I surely should have put that on the first slide.
No, you know who said that sailboats are a hole in the water into which one pours money? Do you know who said that first?
No, I don't.
Jerry
JP
Lewis, the
Who?
comedian,
Who?
Jerry Lewis.
No, he stole it from JP Morgan.
He stole it from JP Morgan.
He did.
Oh, I didn't know that. Good one, good one.
And airplanes are even
He
worse.
says boats in general are a hole in the water that you pour money into.
Compared to those two.
Oh yeah, I like this other joke at the bottom of the first number, first dot. It's the old sexist joke, but it's true. If you go look at the boat shows, there's a tendency to put more money into the cabinets than the hull. The idea there is to sell to women, and because the man is interested in, like the third bullet, how is the deck attached to the hull? Some boat
Very
makers kind of cheat and do it with screws. My boat's a Pearson, which was known for not cheating, and they did it with bolts and nuts. And I've never heard of a Pearson failing, but I'm sure it has. So they're made of fiberglass, and which is that they put the fiberglass in and then fill it with resin, which is really epoxy, sort of like epoxy, and they put it in it, slap it in at different angles to itself, and then they use some kind of suction to pull it through. And the development, my Pearson is one of the latest ones ever made, and Pearson had a year or two before that switched from solid fiberglass to cord fiberglass with balsa wood. And when I learned it, I was a bit upset. I thought they just made it cheaper, but it turns out it's more expensive and it's a better design. As explained here, that the fiberglass serves as like an I-beam, and the boat is lighter and it flexes less. And boat flexing is a very important characteristic of a boat. 0 is the goal, because when it starts flexing too much, one, it doesn't sail well, and two, it'll flex itself apart sooner or later. One of the vulnerabilities of fiberglass is something called osmotic blistering. That happened to a boat I was a part owner of, and I can tell you, it cost me $6,000 to get it fixed. Ugh. And production boats are always use fiberglass, because the basic for a production boat, you build a mold, you put the fiberglass in it, and you've got a hull. Then comes carbon fiber, which is the hydrofoils. It's very expensive, but lighter and stronger, and stiffer. So, and as I say here at the end, what's a couple of $100 million in the grand scheme of things? The next one is aluminum, and there's actually only two. I'll zip through the others. Production boats are always fiberglass, and custom boats, other than the hydrofoils for the America's Cup, are aluminum, because you can shape aluminum any way you want. So if you want a custom boat, they're not going to make a fiberglass mold just for you. They'll make it out of aluminum. And both of them have the problem that if you hit a reef, you're in big trouble, because they'll both get ground into little bits and pieces, and holes will develop. And so now we come to steel. Advantage of steel: they don't make boats in steel anymore, but their big advantage was that if you hit a reef, it will grind the reef into small little pieces, not your boat. Which at the time, it's better just not to hit the roof. And repairing steel is not that expensive. The disadvantage, obviously, is rust. And ferro cement is homemaker type construction. I've never seen one. Apparently, it works pretty well, unless once again you hit that reef. And sail materials quickly are Dacron for what my boat has, and most boats, and nylon for downwind, and performance oriented cruises. Read that. Racers use laminates, which like Kevlar, and I don't even know what the NEMA is. I've seen them. They're kind of impressive, the way there's lots of little pieces and they're sewed together, and basically they hold their shape a lot better than Dacron because of however they put it together. But they cost 2 or 3 or 4 times as much. And hydrofoils, if they're going to go 50 knots basically into the wind, they've got to have something pretty special to hold its shape. And that wing sails is one of them. It's a sail with stuff. There's 2 sails with stuff sandwiched between it to make it something like a wing. And it's all it is money in that case. This one basically says those shrouds and stays, the forces put on the hull are huge, because they're very tight, and you better take them into account, both attaching the plate that the shroud, but shroud is the thing on the side that holds the mast up athwart ships, and the stays are the ones back and front that hold it up from back to front. And here's a little physics for once. These are key concepts. And when you hit heavy wind, the center of effort, the center of mass, they're a point, and the center of gravity. And basically, you're trying to, with the keel, trying to keep the boat not heeling much more than 20 degrees. And there's, depending on how much the keel weighs and how much sail you're carrying, you have different problems. And I didn't want to get to this boat, this picture. I really like this. This is showing the stability of it's basically a displacement hull, and showing that usually my boat would be like this. It increases in stability because it's wide relatively. A racing boat would be relatively narrow to cut it through the water better, the waves particularly. And you get over here, and at this point where it crosses the axis, you have the vanishing stability, i.e., it's going to go turtle on you, as they say. And the inverted stability is very important because, say, for a catamaran, this line would then go directly across, i.e., they have no inverted stability. Most boats, like mine probably, are designed to, if they go upside down, they're designed to right themselves within hopefully 4 or 5 minutes. And that's what they usually consider success. So if all your windows and doors and whatever survive and you continue floating, you'll pop back up and continue on your way. Obviously, they're not going to be as stable, but it's always interesting to me that how they do consider what's called here the inverted stability when they design boats, particularly a boat built for blue water or oceanic sailing. And
Hey, Bob,
yeah, I'll skip heavy weather.
how much more do you have?
Just a couple of slides. I mean, basically, heavy weather means reducing sail, flattening sails, reefing sails. That reduces moves the center of effort down. You can't add to the keel. And the two classic tactics are heave to, which means it's a little difficult to explain. Running before the wind with bare poles is easier with a Jordan Series drogue, which is a rope with a lot of cones on it. And the right length is important because you don't want it to be short. So if you're going down a 90-foot wave, it's shorter than the wave you left behind.
Bob,
And okay, I guess
I'm sorry. Given the time, can you wrap this up in 2 minutes?
Yeah, this is it. So this is the design points. Basically, all it says is ocean cruising. You have a canoe stern, and you tend to have a full keel, and it's narrower. And I repeat the fact it doesn't. They're both aluminum and fiberglass. It's indifferent for any of the uses. And then I was a little surprised how important the book considered a rigid hull. So that says a hull should be rigid because you don't want it flexing itself apart as you sail it, and that's it.